Good morning, everyone. Thanks for coming to see Clint's presentation here. Clint is going to be presenting on his directed research project, which is part of his requirements for the master's degree in earth sciences ocean mapping. But first, let me remind everybody who's on Zoom that this is a basic Zoom meeting and you have control of your own muting, and so I'd ask you to mute and keep the dogs in the background quiet. Put your phones on silent, and if as you go along we have a question, you can raise a hand, and Chris Schwartz, who's running our IT for us today, thank you, Chris, will let me know. So I'm Andy Armstrong. I'm one of Clint's advisors. Clint's other advisor is John Hughes Clark, and he's calling in remotely from the West Coast, so it's very early for him. And that's basically the reason why we're doing this so early, because he's going to get out in the field and do some work. We also have Dr. Peter Ramsey here from Mind Technology, who helped Clint out and was kind enough to loan some of the Sidescan sonar equipment. Clint has a Bachelor of Science in Marine Science from Maine Maritime. Before that, he was in the U.S. Navy as a sonar technician. After school, he joined NOAA to work as a physical scientist hydrographer, and his experience is extensive in hydrography. He's done hydrography or served on 7 NOAA ships, most recently the Fairweather, and his present permanent station is the Atlantic Hydrographic branch, where he's a physical scientist doing hydrographic survey work. Okay, so I'll introduce Clint now and let him tell you about his project on exploring mechanisms to resolve position and intensity disparities to create a combined Sidescan and multi-beam sonar backscatter image. Okay, Clint.
Thank you, Andy. Good morning, everybody. Thanks for coming to my research presentation. So like Andy said, my directed research will be working on, or was working on, trying to get a complete image of Sidescan imagery and multi-beam backscatter for the use of seabed characterization. Just a quick overview. I'll do some background information, and then really get into the methodology and data analysis of how I did this. So as a brief introduction here, the main reason we want to do this in part was based on the presidential memorandum on ocean mapping and the need for characterization and mapping of the U.S. economic zone. And because a large portion of anthropogenic activity does take place in our coastal waters. So it's important to have that characterized. So the main goal, as we stated, of the research was to create a combined surface from the Sidescan imagery and multi-beam backscatter. So what we see here is a typical NOAA hydrographic survey with Sidescan and concurrent multi-beam. So on the top left, you have your Sidescan mosaic. Top right is the concurrent multi-beam lines, and you can see from this image that the Sidescan does a good job of complete coverage, but there's missing information in the multi-beam. And then the bottom image is what we normally see now, the combined Sidescan and multi-beam, where you can still see that there's 2 separate products. And that's what we're trying to fix. So what we have here, really what I wanted to show was the difference in the multi-beam and Sidescan. Just physical characteristics of the beams. So the top image, what you're seeing is a typical multi-beam swath, the single swath, and then 4 lines of multi-beam. And then at the bottom, the top image is a typical single side scan swath in a towed configuration, with the black triangle representing the nadir null zone. So what's important about this is that in that zone, we don't have any seabed information. All we're seeing is the water column based on the geometry of the beams. And so the main reason that we do the concurrent multi-beam is to cover that. The other drawback with the multi-beam is that the beam width the swath width is directly proportional to your water depth. Most multi-beams only cover approximately four times the water depth. So in 10 meters of water, you're getting 40 meters swath width of coverage. Whereas Sidescan, the coverage is dependent on the range scale. So if you run in the same 10 meters of water, if you run 75 meter range scale, you get about 150 meters of swath width. So it's much more efficient to run these Sidescan surveys because you're getting almost 4 times the coverage. And in shallow water, it's just really not efficient, time-wise or money-wise, to try and get full coverage multi-beam. All right, so what we have here, just kind of illustrating that nadir zone on the left. So this is just a typical Sidescan waterfall display. And you can see on the left, we're missing about 30 meters of data in the raw. So that's why we need the multi-beam to cover that. What's important to note is on the right, you see where it's been slant range corrected. So we do the math and stitch the 2 sides together, but there's still really no data there. It's just the 2 sides have been pushed together. So we need the multi-beam to position and fill in that gap. So for multi-beam, the top image is showing a single transmit pulse. We get the wide across track and the narrow along track, and each of these are the individual receive beams. And they're generally configured in this configuration here, which is called a Mills cross, where you have your transmit array and your receive array forming a T. So you can kind of see how that works here with the transmit and the receive. Benefit of multi-beam are the grazing. For bathymetry is the grazing angle. So that's the angle between the transmit and the seafloor. They have high grazing angles, which makes it excellent for bathymetry. There's few acoustic shadows, so the sound is insonifying the full range of those features, and strong echo returns. Whereas the Sidescan are low grazing angles, so when that beam hits a feature, no sound is going around to the backside of that, so you get an acoustic shadow, which does make it good for object detection. So briefly into the multi-beam backscatter. Past generally, typically been called pseudo Sidescan because the image that it receives is corrected similarly to the Sidescan, and what you see is representative as well. So backscatter really for multi-beam is what we call a snippet of each individual beam footprint. It's taking a time series and recording the amplitude of that time series. And the backscatter strength is dependent on the grazing angle and the composition of the seabed characteristics. So like the top right image here, image B, shows typical angular response curves of different seabed characteristics with gravel, sand, and mud. And it kind of makes sense that gravel, it's a harder surface. So it's going to have a higher intensity return. Sand is a little less, is much less consolidated. But what's interesting with sand is out at about 40, 30 degrees, we do get an intensity increase based on the grazing, the physical properties of the sand. It reacts as a hard surface. And then mud, very soft, absorbs a lot of the sound. So you're not getting as much of a return on that. So the main difference, or a main difference between the Multibeam and the Sidescan, or the Multibeam and bathymetry and Backscatter, sorry, is that, as you can see in the top image, the bathymetry shows relief. So you can see the topographic features. And then the Sidescan, all you're seeing is intensity. With no vertical relief. So getting into the data collection, the goal was to collect Sidescan sonar with concurrent multi-beam echosounder data, and that helps by collecting them at the same time. You have the same water conditions, you're covering the same ground. The positioning should, is close to the same as you can get it. So how I plan my lines in this northeast, sorry, in the northwest section here is I ran those lines as a 200% coverage, which basically means that we're insonifying that area of the seafloor twice with the Sidescan sonar. Only one pass of that data ended up being used. Search. And in the southeast, I collected it just at a 100% seabed coverage. So we towed the Sidescan. The multi-beam was mounted on a pole strut, which you'll see here in a little bit. The decision for both of these areas was that the northwest area had heterogeneous bottom characteristics, and southeast was more homogeneous. So I wanted to see the ability of what I was proposing, if it would work in both types of seabed areas. So to help with bottom selection, we used work on CCOM's website, and extensive work has been done to map the New Hampshire continental shelf and characterize it. A lot of work by Dr. Larry Ward here. So the Northwest Acquisition site here, we can see differs pretty greatly. We have a harder substrate and some vegetation, and the other portion is strictly sand, muddy sand. We had no images for the southeast site, but the shades of green just are varying levels of gravel. So you have consolidated gravel and some gravel unverified, and that work was done analyzing various backscatter from different surveys that have been collected. So this is a summer hydro survey done here at CCOM W00501. And this is the backscatter that resulted from that. So now we can kind of see the intensity levels with that rocky area and the sand. And then down here, we can see it's pretty homogeneous. Just, you can see vertical relief, but it's all gravel. So the systems that I chose to use, I met with Pete Ramsey, Dr. Pete Ramsey from Roxy, you're drawing on the screen. So the systems I chose to use, before I began my project, I met with Dr. Pete Ramsey and the team at Mine Technology. I initially wanted to use a Klein 5000 sonar, which is one of the two main sonars that NOAA uses. But we determined that for this research, their brand new 4K SVY single beam side scan would work best in the frequency matching with the EM 2040, Kongsberg EM 2040, both generally collecting at the same frequency of 300 kilohertz. So that making the intensity values match would be easier. So here we have the Klein as mounted on the research vessel Gulf Surveyor with the tow cable. And this is the EM 2040 on the right, mounted on the vertical strut that is able to be lowered through the moon pool.
Oh, my gosh. I can't clear it. Great.
She needs to log out.
So Fairly's gone down.
Thanks, Early. So the first thing I wanted to look at, as I felt this was the most important part, is getting the positioning of the two sensors of the two images to be in the same location. So what we can see here is there's multiple uncertainties involved with a towed system. First off, you have to accurately measure, the offsets between your vessel reference point, which on the Gulf Surveyor is about here. We use the reference point of the ship. There, all back to the tow point of the A-frame when it's been extended. You have to know your cable out and that layback value, which determines the layback value to the fish. So what you can kind of see here is, the fish isn't always this nice, it's almost never this just nice, beautiful triangle that would make it very easy to know where it is. Depending on ship speed, currents, any number of factors that are occurring, towfish could end up forward or aft and also up and down in the water, vertically in the water column. So we want to be able to correct for that. And also with currents, if you have a strong current coming from either side of the vessel, that's going to affect where it's at in the cross-track dimension as well. So to help correct with that, I used Sonar by Chesapeake Technology and their tool called Map Corrections. So what Map Corrections does is it takes a known, quote unquote, the known true position of a feature in the multibeam, and then the position of that same feature in the Sidescan. And what we can see here in this image is the blue markers represent the true multibeam position, and the green markers are where the Sidescan, that same contact in the Sidescan. As an example, here on the left, we have this is all the same contact. We have that contact in the Sidescan. The middle image shows the distance between, or the offset between where that contact was in the Sidescan and where it is in the bathymetry, which in this case was about 10 meters. And on the right, we can now see that same feature is positioned fairly precisely with the multibeam position. So what we're seeing here is the southeast site, and we see examples where this didn't quite work. And this is mostly due to the lack of finite features due to the nature of the survey. The multibeam just wasn't quite wide enough to show a lot of features in the data. So after both lines have been corrected to their responding multibeam, and we can see here that they line up fairly well with their multibeam. They're still offset with each other. To get around that, you could, if you're doing a 200%, technically you shouldn't. You want to use the same multi-beam from the same lines that you're collecting your side scan. But you could use, you know, if the sand waves extended a little, if you had more features, you could select more points. It's just an inherent disadvantage with this type of survey and this type of correction. So what we're looking at here, on the left is the raw side scan prior to having any gain normalization or map correcting position corrections done. And what we see is what appears to be two distinct lines of lobster pots and one distinct rocky area. After the map corrections, we can now see that that really was just one singular feature. This guy here is its own, it's not an artifact. And you can kind of see it, it shows up double on the left. But what's more important actually is that instead of one singular feature up on the top, it's actually two different rocky areas. So you have two different seabed characteristics, where before you might have thought there was only one. So what we have here, this is the Sidescan mosaic prior to any map corrections or gain normalization. And in line with the bathymetry. And we can see several areas now where they, you know, we can tell that they don't quite match up. If you pay attention to the area to the southeast where there's a strong feature, and also right in the middle. And if I go back and forth, you can see how those are definitely, you can definitely tell that those are out of position. Moving forward, this is now the same Sidescan mosaic, but it has been map corrected. Looking at those same features, we can now see that those positions are very accurately located. So if we go back. So getting into the multi-beam, use QPS, Fledermaus Geobox Tool Coder, FMGT to process the backscatter. I followed NOAA's standard backscatter SOP. And where I diverged from that is in the top left, this is our standard backscatter product, showing the range of backscatter intensity at a default 10 to negative 70 dB or decibels. And the top left is the Northwest survey area, and the top right was the Southeast survey area. And in the bottom in the middle, I adjusted the backscatter to match or to better show where the boundaries between high and low contrast seafloor characteristics are. The other diversion I made was that when we create site backscatter mosaics, we use a set resolution that's completely dependent on the frequency of the sonar used. In this case, would normally be a 2 meter resolution. And I chose to do 50 centimeter to match the side scan resolution as well. So here we have the side scan on the bottom with its default intensity levels, and the multi-beam backscatter that had been adjusted to show the high and low contrast areas better. The side scan at this point has been gain normalized and corrected for position. So here we have, once the side scan has been adjusted for intensity, with that same multi-beam backscatter now on top. What we can see here is not only is it accurately aligned in position, but now the intensity values are very well matched. They're not perfect. Work can be done. This was the goal. This is the end product. This is what we wanted to see. And it's my belief that this is a much more worthwhile product than this. So my conclusions, after being corrected for position and intensity, it's a worthwhile product. There are some limitations, like we saw with the Southeast survey site, difficult to match both and in position and intensity. That's just due to the nature of the seabed. It's homogeneous, lack of features. Some other limitations, the backscatter values for this were not represented in the same units. The Sidescan was represented as a base intensity level voltage, whereas the Multibeam was in decibels. So that kind of results in more of a qualitative, subjective product. And using these same things, different users could end up with a slightly different result. It's almost an art form, being able to recognize contrasts. But I do believe that despite these limitations, we're still meeting our philosophy. Ping once, used many times. It's a valuable tool for anybody in ocean science. It's definitely worthwhile to NOAA to invest the time and resources to create this product. So for my research, I'd like to acknowledge Captain Andy Armstrong and Dr. John Hughes Clark for being my advisors and being very patient with me throughout this entire process. I'd also like to thank the rest of my professors and fellow colleagues here at CCOM for their valuable information. I'd like to further thank Dr. Pete Ramsey of Mind Technology for the use of the 4K SVY Sidescan and his expertise. He's been a great help throughout this as well. And Patrick Zinda from Chesapeake Tech provided amazing support throughout this process. And I really want to thank my fellow graduate students here at CCOM, particularly Lieutenant Patrick DuBois and Lieutenant J.G. Arley Pickett. They were just always there with support and editing. I'd like to thank Dr. Larry Mayer, Director of CCOM, and those at NOAA's Office Coast Survey who made this entire thing possible by showing faith and selecting me for this opportunity. And lastly, I'd like to thank my mom, the rest of my family, never giving up, and to my dog Bailey, who really put up with moving up here from Virginia and always welcoming me home. These are my references, and thank you.
Okay, so we'll have an opportunity to ask some questions here of Clint. First, let me ask John, who's calling in. John, would you like to ask your question?
Yeah, thanks very much, Clint. And I think this is a directed research project, and it reflects a potential change in NOAA's operational requirements. But I think one of your last words worried me, that it's an art form. I actually agree with you, but I thought it'd be worth looking at some of the things that you showed that I don't think in the current, and again, you were mandated to use operational tools that exist, software tools, not to build your own new set. So there were a couple of things that, well, it's been, if we go to the actual normalization of the backscatter, if you just want to jump to one of your early slides where you showed the multibeam bathymetry and backscatter, way back. Keep going. or you just go out and click. It's about 4. That keep going back. Keep going back. Early on. Back. It's just at the beginning where you just have multibeam bathymetry and backscatter. That one, yeah, super. If you look in the bottom one with the backscatter, you see you're barely able to tell the ship tracks, and yet you show in the right-hand figure that there's a strong angular response curve, and that is actually being taken out by 2 organizations. One is the provider of, in this case, it happens to be Kongsberg. They have an algorithm that flattens that curve, but it doesn't do it quite perfectly because it's based on assumptions. And then the package you use, which I believe was Chimera, and they've also hidden that. But if we look at the boundary between the high and the low backscatter, if you look carefully, and ooh, I could do a Roxy and write all over your screen somehow, but you'll notice that there are funny changes at the boundaries between the sediment type, which aren't real. Could you comment on what they are?
I can't.
Take a stab at it, Clint.
It's a gain function.
I would say that it's a product of the algorithm.
Yeah, I mean, it's
beam, basically beam pattern corrected. Those boundaries, they're not normalized the same.
Yeah, I mean, it's beam pattern and that angular response curve, and I strongly suspect the Sidescan companies are doing exactly the same. It's hard to separate the two, so they're looking at the response across the swath, and it works when you're in one sediment type or the other, but when you cross a boundary, you get all these artifacts. And so this is something, and I was wondering, when you used Chimera, did you have any control over that? Do you have choice?
With FMGT, there's really, following our procedures. It's doing all the work on the back end or on the front end and behind the scenes. And the only real options we have are changing resolution. There are options. There is the availability to go in and adjust the coefficients manually. I haven't done that personally, so I don't know how that would actually affect those boundary disparities there.
Yeah, because that impacts the image quite a bit. The other thing, I'll ask one more question to hand over to Andy, and I can come back with questions. But the positioning that you identified, you showed Anna Crawford's figure there. Yeah, that one. And although you mentioned those were available, we navigated to the toe point offset and then layback. But the choice of what to do with the layback is algorithm dependent. And I just want to confirm, I think you accepted the Klein or whoever owns the mine algorithm.
Yes.
And so they had very good cable out, and yet you had those offsets. Did you have any details on how they apply that layback, as whether, for example, when you're crabbing, do they lay back along the course made good, or do they lay back along the ship's azimuth? Is that something you could see in the manuals?
Yeah, as far as I remember, I want to say it's along the course made good. So basically, basic trigonometric cart and horse style calculations for that layback.
I mean, I think it would be.
John, maybe I should just step in here a little bit. Yes,
Absolutely. I was about to ask you. Yeah.
It's a standard Pythagorean thing, but you would never get a 10-meter longitudinal offset with a short cable like that in that water depth. So I read from that the calibration of the cable counter was out.
Okay.
And that's the reason you've got to run the cable through it, marked cable, and make sure you're getting the same numbers as the markings are giving you. And there's a factor that you actually input into the cable counter. And I can tell you now, I think it was wrong, because you would never, ever, with any layback algorithm and a short cable, you would never get a 10-meter difference in the longitudinal offset of a towfish. So there's your answer.
Yeah, and it might even be a cross-track offset, which makes me wonder, because we were crabbing quite a bit. I think, I mean, for Clint, I think, again, it's this art form. If this is going to be operational for NOAA, there's that layback calibration. It sounds like it's human error here. We've all done it. But then there's Sonar Whiz. Again, you can apply it in another package. Each one of these is a contribution to the error source.
Yeah, other packages do provide that intensity as a decibel, so you'd be working in the same units, at least, which would definitely make it less qualitative. But I think without some serious work, some actual, thesis style work to get into the coding on that, I think, this is kind of where we're at right now.
And well, I think the positioning is a concern, and the last thing on the positioning is you showed rubber sheeting, but is that practical for operators in the field to spend time lining up targets? Because that's
right, and that's something
very human intensive.
Right, and I think that's a decision that would have to be made above me. I feel it's worthwhile to be done, whether it be done at the branch or at the processing branches or on the ship. I feel it would be something more done at the branch, personally, because it is right now time intensive. Once we had it, figured out, I think it's a relatively simple process. So it could be done on the ship and delivered as a product.
Thank you, Andy. I'll hand to other people.
Okay, I'm gonna ask Pete if he has any questions at this point, or
Just a general comment, Clint. You tackled something which I don't know if you realize is incredibly complicated. I mean, if you were just trying to compare two different multi-beam systems, you would have had just as big a headache. But here you're trying to compare something with completely different grazing angles. The package that you used did not give you decibels. That's a Chesapeake issue, which I hope that they'll address at some stage. So you tackled something that was really, really difficult to do. And, kudos to you. And you've produced a really good result. Just from a practical point of view, positioning is going to be a big thing, and it's going to be one of the biggest bugbears to getting this right. And John's right. I don't think from an operational point of view, people are going to have to sit and rubber sheet. So my suggestion is that we're going to draft a basic SOP for doing this, that you have a cable counter SOP system, but please do what we do in the industry. So you don't rely on one source of positioning for your towfish. A really good USBL, combined with an INS system, they're reasonably priced these days. I would have that on there, combined with a cable counter layback. And in software like Chesapeake or any of the others, you can do a blended solution, a blended positioning solution. So occasionally your USBL will be a little bit flaky due to bubbles in the water or something like that. And you can stitch in that bad, uncertain, positional uncertainty information with cable counter and standard layback.
Okay.
So does mine sell that kit?
We don't make them, but we do sell them as packages here. Yeah. So but otherwise, great job.
Thanks.
I think you'd be very proud of what you've done.
Thank you.
Just give me a hard time. So I've asked all my questions offline with Clint. So I'm going to open up at this point to any in the room. I see Val is raising his hand.
Clint, I thought you did a great job.
Thank you. You had your chance last night.
I know. And I have some comments and some questions too. Some about some of the things that John brought up. So I don't know if he still is, but Dave Finlayson used to be the lead software guy at Chesapeake
Yeah,
Technology.
he worked with me a little bit too. Yeah.
Yeah, and he worked at USGS prior to that. And he was a big ME Systems user. And we talked about last night a little bit about the quote unquote rubber sheeting. But as you pointed out, it's not actually rubber sheeting. He's adjusting the navigation of the towfish and then just laying everything back out, not kind of the traditional rubber sheeting.
Right.
Yeah, and and that's exactly what ME System does for underwater kind of stuff. And I suspect that he got the idea from there. But my thought was that I would bet he's adjusting the positions of the towfish, but maybe not correcting the heading of the towfish. And it may be that you can't do that. It might be like one too many variables that is difficult to solve for. And I wonder if that's why you see the offsets at the edge of the swath after you've done all the corrections, that there's heading biases from towfish in opposite directions. I don't know if that's the case, but I thought I would mention it. The other thing that they do is that's different than FFGT, I think, is that John was talking about the boundaries of the backscatter and how there's artifacts there after the normalization process, and FMGT does that processing. And I think that's because they go along the time series of the backscatter data and try to normalize things relative to like the last 100 pings of what they're measuring. And what I think SonarWiz does is they take your entire Sidescan data set and they shove it into a big database, and that's not based on position anywhere. And they look at, for all the grazing angles of a particular amount, what's the range of backscatter values you got in there, and then they do a normalization process that's sort of global.
Right.
And so you might not see those artifacts in the corrections after.
So how I applied the what they have now is empirical gain normalization. And so you take one line, build your beam pattern file from that line, and then apply that to the rest of.
And you choose a line which is has a lot of
Have a
different
lot of
sediment
contrast
types
in it, right.
Contrasts, yeah.
Yeah. So that's kind of a different process, and so you'll get different things. So here's my question, actually, we'll finally get to that. So in the process where you did, I think the term you maybe used is contrast normalization or stretching to match the two sonars.
Mhm.
Can you describe that process of like what you actually did? Is it something that's automated or something that you like dialed numbers around and visually match them, or
Visual, it's a visual matching and you know, stretching the histogram.
It's a histogram normalization.
It's a histogram normalization.
okay. So you just sort of stretch it and maybe adjust the amplitude a little bit so it sort of looks
the same.
but not really anything quantitative
Right.
in that effort.
Right.
I was afraid of that.
Yeah. That's why I say it's definitely qualitative and not quantitative for the intensity matching.
Thanks.
That's where, if John's still here, that's where I was getting to with the art form, that visual matching.
Well, so let me come in with a question now. So do you see a prospect for that getting less arty and more quantitative?
I could see that. You know, and again, it does depend on the in this case, and the software used, I think. But I think you could definitely do the work to make it quantitative using the, you know, the values from each system and doing the math on it.
Hardware manufacturers would have to be a lot more open too.
Right, because you would need the receiver sensitivities in order to make that transformation. And that's pretty proprietary stuff usually.
Okay, anybody else in the room? We'll go to the room first. Yeah, Patrick.
Sure. So you diverged from the NOAA operations by changing going from a 2 meter grid to a 1/2 meter grid. So 2 questions. The first one, did you do it in 2 meters? And if so, was there a major time difference in the processing time? And do you think you could get a similar set of results as far as how good it looks?
So I
compared to the 2
did,
meter?
there was no significant time difference. For this, it was super small.
Sure.
So I think the 1/2 meter grid was only like 20 meg. So it's a super small area, so no significant time difference. The resolution made a big difference. And I should have, if I thought about it, I would have included that.
So you don't necessarily think you could end up with the same product at a 2 meter grid? You would have
I think you
foresee
could.
NOAA having
I
to
think
say,
you could.
hey,
I think you would just have to do more adjustment visually of the histogram. But you wouldn't. 2 meter versus 1/2 meter. You're not going to get the fine edges and the boundaries. But as far as the intensity levels matching for the backscatter stuff, yeah, I think that 2 meter would still work.
Fairly?
Another operational question. Time-wise, how much time, but you said you thought that it's feasible for NOAA to do this. About how much time does the actual matching take? For after you figure it all out?
So if we
Take away the training time.
take away the training time, really it depends on how good the positioning was to start with, and then how many features you have. There I had some lines I only had to do 1 feature, and then the whole line was great. Other lines,
So it depends on how straight someone is driving the boat.
well, no, not necessarily. It depends on how good the position of the fish is. Like if you have if we had a USBL and we had the correct offset, this probably, I don't know what the results would have been.
You still have the intensity piece.
Right, you would still have the intensity piece, which that wasn't time intensive really.
Okay. So the intensity piece wasn't time intensive. It was the positioning.
It's the positioning.
So potentially we could just at this time do away with the positioning and just go solely with the intensity.
But you
No,
wouldn't,
which is
but they wouldn't match.
Right.
They wouldn't be in the same position, which is why that was such a big part of it.
Just from an industry point of view, a lot of experience doing this type of stuff. When you're comparing multi-beam features to side scan features and you've used a blended solution of cable count and USBL, and you're working in, let's say, sub 100 meters water depth, your side scan should be within 1 to 2 meters. So any feature in that side scan should be between 1 to 2 meters of what you see in the multi-beam. That's pretty much a rule of thumb.
Well, that's when you're operating it, Pete.
Yeah.
I want to build off that. So if you're looking at the ship versus office or whoever doing this, right, is the algorithm the time sync for the positioning, or is it somebody going through and selecting targets in both systems?
It's the manual going through selecting targets.
There's a good research project.
Yeah, write that up.
Who are you looking at?
Everybody.
Are we talking about machine learning here? Is that what's,
Yeah.
I have one more question.
Mhm.
So did you do everything in Chesapeake? Or did you?
So I
some
processed the
of it in-
side scan in Chesapeake, backscatter, the bathymetry was processed in Chimera,
Okay,
and the multi-beam backscatter was processed in FMGT.
Okay.
If I had more time, Chesapeake now does do everything. It's a full package.
but then you don't, but Chesapeake doesn't give you intensity.
Not in decibels, right?
Could you take the product that you get from Chesapeake and put it back into? No?
It's not a floating point. I tried.
Anybody online, Chris?
Yes, We have, I believe, two questions. One from Evan Robertson. Nice presentation. Did you look at both SSS frequencies? Did the low frequency provide a better result as it was closer to the MBES frequency?
So we chose, I did not do an analysis between the 300 and 600 kilohertz of the Sidescan. I briefly looked at the 600 because I had it. But I didn't actually do any analysis on that.
And another one from Guy Knoll. I think this is more.
Hello, Guy.
I wonder if the tools used for panchromatic or multispectral satellite data analysis may be useful for automating the normalization with sonar in this case. Sorry if I butchered that.
No. I don't know.
And another quick one from Tom Renata. Do you use confidence checks for SSS positioning?
So we did start off doing a confidence check slides, but we did do confidence checks for the Sidescan prior to data acquisition.
Could you talk a little bit about the Sidescan confidence check and that you did? What is that process?
So the process there is we selected a target and ran a set of lines perpendicular to each other at a set spacing around that target at a 50-meter range scale, because that's what we were using for the Northwest acquisition site. And then using the same, take the error or the distance from the multi-beam target to the Sidescan target and do a 95% confidence of the radial error. And then based on NOAA standards for a towed position, we're allowed 10 meters of that for that radius. And everything was less than that.
Explain why that standard is so big. We were talking about it last night.
Or
Yeah, I was like, 10 meters is a huge amount of error. And you're like, oh, because.
thanks, Val.
Do you remember last night?
No.
So many hours to do.
So for
If you
a
find
keel
something-
mounted system, we get 5 meters because we know that position very accurately.
So what do you do if you find something?
So we just need to know the general vicinity of where that target is, because we then go back and develop it with the multi-beam and get the accurate position. So a 10-meter radius is good enough for multi-beam or a diver if we do a diver investigation.
Another error that you can have with cable counters is what I call cable jumping. So depending on the angle from the winch up to the sheath block and then down, if that's not a very acute angle, you can get the cable actually lifting as you go through swells. The cable lifts off the cable counter and then spins.
Right.
And you'll find that gives you a lot of error. And generally a good idea to, every time you pull the cable in and out, to reference it to the marks that you've made on the cable, just to make sure that hasn't happened. Your winch is at the top.
Yeah.
Right. So that's a really poor angle for that type of jumping. So that can be another error. So you might find that when you've calibrated your cable count on the first couple of lines, it's in. And then as the survey progresses,
Get some slippage.
you get slippage, and that will easily add up to 5-10 meters.
That's a good point.
So again, that sort of angle like that is the angle that you want, because that mitigates slippage.
Thank you.
Okay, nobody else on? All right, last chance.
I got one more
Yep,
short one.
that's why we bring Val in.
Yeah.
So like you were kind of lucky in the sense that you had resources that you could match frequencies with the multi-beam and the Sidescan. When you think about your experience in the NOAA fleet, do you typically have Sidescans that match your multi-beam frequencies? No.
Well, they would have been closer. The Client 5, we normally either use a Client 5000 or an Edge Tech. So 455 kilohertz is pretty close to what we would run at 400. So with the multi-beam, that would be close enough. Or closer.
Depends who's asking probably,
Right.
but so to make all of this worthwhile, really means you got to procure the systems that are going to match in frequency, so that when you blend them together, you have an apples to apples kind of merging, and you're not measuring two different things and then trying to. That's
More than that.
yeah.
Yeah. No. And that's
Well, wouldn't, you could still do the positioning.
Yeah, that's right.
Right.
But you wouldn't want to take backscatter at 400 kilohertz and Sidescan
No.
at 300 kilohertz
Right.
and put those in the same image.
Yeah.
It would just make no sense. They should look different, and you wouldn't want to normalize one to the other because you're just making things up.
Yeah. So I do hear-
John, do you have any final questions? John's still there?
Yeah, I guess just one last comment. Suppose we go to all this effort, then I look at some of your images and I see thermocline artifacts. Is this helping the nation if we map the water mass and not the seabed? Facetious comment.
no. And I did mean to talk to that as well. That there was a lot of refraction in this area, which obviously affects the backscatter of the Sidescan.
And the solution to that?
Wait till the oceanography changes or.
Yeah,
Or change the ratio.
or change the range scale.
Yeah. That's the range.
I mean, that was already a 50-meter range scale, so it was already in pretty close.
It's tough in shallow water. In deeper water, you can move the towfish up and down a little bit. But in 10 meters of water, there's not much up and down space.
But Andy, this is one of the worst areas I've ever seen in the world for this.
Here in Kotzebue.
It's just,
Well, I have to say the worst area I've ever seen is the approaches to Chesapeake or to
D304.
Delaware Bay.
Yes, they're terrible.
So there's lots of places.
It's so bad.
Yeah, anywhere where you're going to have that freshwater influx.
Or
tidal.
when the weather's really calm and it's sunny and the water
you get the
heats up.
surface layer. We saw that in Lake Huron.
Yeah, it was brutal.
Yeah, so this is exactly, it's going to be a limitation to anything you do with Sidescan. Okay, well, let's thank Clint again.
Everybody.